Okay, so this example is going to be considered as one of the most challenging examples that we have through this semester. Mainly what we have in this example is a bar AB is going to be falling down from the height of 0.5 meters, and then is going to be hooked at its end A with the hook S. So after this touch is going to change the movement from a linear movement into an angular movement. So in that case, we get three states, 1, 2, and 3. And to find the equations for that, we need to do the analysis into three stages. First one is going to be the conservation of the energy between the state 1 and the state 2, or 1 and 2. Then we're going to have the angular momentum conservation between the point S and turning to the angular momentum. And the last one is going to be the conversion of the energy again between the state number 2 and state number 3. Okay, where it's going to make a rotation around the point S. So let's get some information from here. The 2 kilogram is the mass. The length is 1 meter. The height 1 was 0.5 given to the height of 0. Then it's going to be dropped down with the point G to the height of minus 0.5. We need to find the speed at which the other end B will strike the wall. So we're going to find the omega at this state. I can find the velocity, which is going to be equal to the omega multiplied by the r between the S and the B. So we start with this calculation. You can see that the difference between this question and the one before was that it was moving linearly, and then it's going to change when it's going to be hitting here. It's going to change to the rotation of the point S. Okay, and we can apply the same equation later. So anyway, let's have a look to the answers that we have. You will see that the solution will find first the speed of the rod's mass center just before the impact at the S is going to be determined for the conservation of the energy, putting the datum point at the bar initial position, and we're going to have the T1 plus the V1 equal to the T2 plus the V2. From that, we will solve to find that the velocity at the point G will be equal to 3.132 meter per second. And then the angular momentum is going to be conserved about the S by considering that the weight as the non-impulsive force just before and after the impact will be happen. So the HS1 is going to be equal to the HS2, and from that we will find that the omega2 is equal to 4.698 radian per second. After that, when we're going to have rotation about the point S to the final position or the fourth position, we will use the conservation of the energy again with the datum point of the bar at the bar horizontal position, and we're going to have that T1 plus the V2 is equal to T3 plus the V3. And thus we're going to find that the omega 3 is equal to 7.176, and then we can find the value for the velocity at B by multiplying this value by 1 meter. Okay, so let's go back and try to solve the problem step by step. So first we define that we have four states can be identified. The first one is the initial. So when it was at the 0.5 height, it's going to be dropped down as a linear position. At the state 2, immediately just before the end A is going to be strike the hook S. And here what was rectilinear translation, and then we're going to have the rotation to be happening between state number 3, which is immediately after the end A strike the hook, and then is going to move to the state number 4, which is immediately before the end B strike the wall. And this will be rotation about the fixed axis through the S or the A point. So these are the four examples. From 1 to 2, we're going to have the conservation of the energy. We can calculate the T1, the T2. We can calculate the V1 and the V2. And then we're going to have that the HS1 is going to be equal to HS2 between state 2 and 3 to find the velocity at the point G. Then between the state 3 and 4, we're going to go back to the conservation of the energy. So the diagram will show us the state. This will be state 1, is going to be dropped down to the height of 0.5 meters. This will be the state 2. That's at one point. Then from the state 2 to the state 3 is going to be hooked down here. And from the state 3 to point 4 is going to be having a rotation about the point A. So from the state 2 to the state 3, we're going to have the equation is going to be that the mass multiplied by the velocity of the point G2 plus the conservation we're going to have here for the momentum, the WT, and we have the force at the point A going upward is going to be equal to the IG omega 3 plus the mg mvg 3 multiplied by r. So exactly like what we done in the previous question. So we know the mass, we know the velocity at the beginning was equal to 0 because it was at state. The omega 1 is equal to 0 and the omega 2 is equal to 0 because it was linear movement. The y2 is going to be y1 is 0.5 meters, the y2 and y3 is equal to 0, and then the y4 is going to be equal to minus 0.5 for the point G. We need to know the Vg4 and the omega 4. So the equation we're going to use from 1 to 2 is the conservation of the energy. From 2 to 3 is going to be conservation of the momentum. From 3 to 4 is going to be the conservation of the energy between state 3 and state 4. So 1 to 4, 1 to 2, and 3 to 4 is going to be only conservative forces. The gravity force does work. From 2 to 3 is going to be comparing the impact forces at the hook S, and the gravity force W of the road is non-impulsive. And 2, the angular momentum around the point S is going to be conservative, and the P is going to be eliminated. So we start with the state number 1 to 2. T1, or T in general, is going to be half of the mass Vg square. And the T1 is 0 because the omega was 0, the velocity was 0. And then the T2 is going to be when we're going to move for 0.5 meter downward. So this equation can be written now as the 2, which is the mass, multiplied by the Vg2 square, and this will be equal to Vg2 square. Now for the V1 is going to be the weight multiplied by the Y1. The V2 is going to be the weight multiplied by the Y2. The Y2 is 0. The Y1 was 0.5. So the 2 kilograms multiplied by 9.81 multiplied by 0.5 meters, and this will give me 9.81 joule. While the V2 was 0. Well, we know the T1, T2. Just put that in the equation. Okay, and by solving, we will find that the Vg2 is going to be equal to 3.132 meter per second. Done. Now we go to the next step, which is going to be the conservative momentum equation, or the HA1 is equal to the HA2, or actually it's going to be 2 and 3. So the HA is equal to the Ig omega plus the mass multiplied by the velocity multiplied by the RGS. So I need to calculate the RG here. It's 1 over 12 multiplied by the mass of 2 multiplied by the length of 1 meter. So we can find that. Again, in the state number 2, the omega should be equal to 0, yet the Vg2 is already being calculated. The omega 3 is unknown, and the Vg3 is unknown. Anyway, we're going to start to put the equation. So the Ig multiplied by 0 for this part, because omega 2 is 0, plus the mass of 2 multiplied by the velocity of 3.123 multiplied by 0.5, which is the RGS. And this will give me the answer to be 3.132 kilogram meter square. Now we go to this side. The I is 1 over 12 mass length square. What else do we know? Omega 3 is unknown yet. Okay, but the velocity here can be written as the omega-3 multiplied by 0.5 meters, right? So we can substitute that. So by putting that together, the omega-3 and the omega-3 RGS multiplied by the RGS, so this will be squared. We know the RGS is 0.5, the mass is 2, and thus these values should be equal to each other. So we will end up by knowing that the whatever the omega-3 value is, which is going to be by adding all that together, to be 0.667 omega-3 is equal to 3.13132. And thus, we can write the omega-3. So we come to the equations here. Solve for that. We'll find the omega-3 is 4.7 radian per second. Now let's go back to the state 3 to 4, which is going to be the energy conservation equation. Again, the T is going to be half of the IS omega square. So what changed here? Because we're going to have pure rotation, okay? Angular energy is going to be applied. So here for the IS is going to be 1/3 mass multiplied by the length square. The omega is going to be the omega-3 and omega-4. So in state number 1, we're going to use the half of the IS omega-3 square, and the state 4 is going to be equal to the half of the IS omega-4 square. Now the IS can be substituted here. The omega-3 is known, so we find that the T3 is equal to 7.357 joule. And the T4 is going to be in terms of the omega-4 as 0.333 omega-4 square joule. Now we come to the V. What's happening is that the center will drop down by 0.5 meters negatively, and thus the first y is y3 is 0, the y4 is minus 0.5. So we can simply apply the equation for the V, and we will find that the V4 is going to be equal to negative 9.81 joule. So now we know the T1, T2, we have the V1, T3 and T4, the V3 and the V4, we put that in the equation, and we will find that the omega-4 is equal to 7.18 radian per second. Okay, now once again, we're going to go through the question in the classroom step by step, and we will find more details about the solution